Alright, so we're looking at 8.3, and 8.3 talks about relative rates of growth. This is looking at functions that are growing faster than other functions and comparing rates of growth such as that. Now, the function y equals e to the x grows very fast. We could graph it on the chalkboard, and if we did, we would find that if x is 3 inches, y is about 20 inches. Now, at 10 inches on the x-axis, so if x equals 10, y equals 1/3 of a mile. That's a lot of inches. Well, not only that, but at 44 inches, the y value would be 2 million light years. Now, we've gone less than halfway across the board horizontally, and already the y value would reach the Andromeda Galaxy. That gives you an idea of just how fast this thing grows. Now, not only that, but at 64 inches, the y value would be at the edge of the known universe, about 13 billion light years. That's just if we're talking about inches. 64 inches, that's what the y value would be. It would be the 13 billion light years in inches. That's a big number. Now, the function y equals natural log of x grows very slowly. Of course, remember, it's the inverse of e to the x. So all those x and y values are just going to flip places. So if we graph it on the chalkboard, it looks like this. We would have to move 2.6 miles to the right before the line moves a foot above the x-axis. And by the time we reach the edge of the universe again in the x values, the chalk line will have only reached 64 inches above the x-axis. So just to give you some things that'll kind of melt your noodle there a little bit. Now, the function y equals natural log of x increases everywhere. It's constantly increasing. But it increases pretty quickly here at the beginning, but as we notice, what happens? It's going to get slower and slower and slower with its increase. The slope of that thing as x goes to infinity approaches 0 but never gets there. Alright, let f of x and g of x be positive for x sufficiently large. F grows faster than g, and g grows slower than f as x approaches infinity if the limit as x approaches infinity of f of x over g of x equals infinity. So if you take the limit as x goes to infinity of one function over another, and that limit is infinity, then the top function grows faster than the bottom function. And thus the bottom function grows slower than the top function. Or, if you flip those, if the limit as x approaches infinity goes to 0 of one function over another, then the function on top grows slower than the bottom, and the function on bottom grows faster than the top. Now, f and g will grow at the same rate as x approaches infinity if the limit as x approaches infinity of one function over another equals L, which is some number that's not equal to 0. So if you end up getting a constant for your limit, then your two functions grow at the same rate. Now, here's a warning. Temporarily suspend your common sense for just a second here. According to this definition, y equals 2x does not grow faster than y equals x. They actually grow at the same rate. Now looking at the graph, you can see that this one does technically grow faster, but we're talking about a weird different definition of growing faster. Now, the way the book defines it is that if f grows faster than g, this means that for large x values, g is going to be negligible compared to f. For instance, like when we talk about limits going to infinity and we talk about x and 2, remember the 2 is negligible as x goes to infinity. Well, in this case, the same case is true. It has to grow dramatically faster, not just by a multiple faster, but I mean grow at a faster rate for it actually to grow faster. So easiest way to remember that is grows faster is not the same as has a steeper slope. Alright, so which grows faster, e to the x or x squared? Now you probably can already answer this, but let's go ahead and go through the steps of proving it. So if we take the limit as x approaches infinity of e to the x over x squared, well this of course is going to be infinity over infinity. So this is indeterminate, so we're going to apply L'Hopital's rule. When we do, we're going to get, of course, e to the x again on top, but 2x on the bottom, which is still going to approach infinity over infinity. But as we continue and apply L'Hopital's rule again, we're going to find we get e to the x over 2, which of course is going to go to infinity. Therefore, we've just proven that e to the x grows faster than x squared. Now we can confirm this graphically by graphing e to the x over x squared, and of course that's going to take off to infinity. We literally just graphed exactly what we were taking the limit of, and we're looking for what happens as x gets larger and larger and larger, and then this goes off to infinity. Now, growing at the same rate is transitive. If you don't remember what transitive means, that means if two things are growing at the same, if two things are equal to another thing, then they're equal to each other. And the same thing is applicable to growing at the same rate. So in other words, if two functions grow at the same rate as a third function, then those first two functions grow at the same rate. So if you can prove that two functions grow at the same rate of a third function, then you've just proven that those first two functions, the original functions, grow at the same rate as each other. Alright, so example 4. Show that f of x equals the square root of x squared plus 5 and g of x equals 2 square roots of x minus 1 squared grow at the same rate as x goes to infinity. So first of all, we're going to let h equal x. H of x equal x squared. just x. And we're going to use the transitive property to prove that. If we can prove that this grows at the same rate as x, and this grows at the same rate as x, then we've proven that these two grow at the same rate of each other. So let's take the limit as x approaches infinity of the square root of x squared plus 5. Well, of course, as x goes to infinity, the 5 becomes negligible. So we end up with the square root of x squared. Or we can do it this way. And in this case, this is a little longer version, but we can do the x squared on the bottom. The square x is nothing more than the square root of x squared. We know that. So now, if we did this and put this fraction together, remember we can divide this into both parts up there. So x squared into the square root of x squared gives us x squared over x squared. And then 5 divided by the square root of x gives us 5 over x squared inside the radical. Then as we take the limit, what's going to happen? Well, this is going to equal 1. This is going to go to 0. So we end up with a limit of 1. All right, if we do the other one, we have 2 square roots of x minus 1 over x. Do similar to the same thing. We're going to express this x as the square root of x squared. Divide that into both parts. So we end up with 2 square roots of x over the square root of x. Because we can, since they're both raised to the second power, we can move this inside of that fraction there. Minus 1 over the square root of x. And of course, these square roots of x's would cancel out and leave us with 2 minus 1 over the square root of x as x goes to infinity, which would be 0. So we end up with 4. Now, it does not matter that these two numbers are not the same. Remember, all we need is a non-zero constant to prove that they grow at the same rate. So by the transitive property, the limit of f to g is the same thing as the limit as x approaches infinity of f to h times h to g. This is a analytical version of showing what the transitive property says. And when we do 1 times 1/4, we're going to get 1/4. It's a constant multiple that is, or a constant value that is not equal to 0. Therefore, these two grow at the same rate. Now, you don't necessarily have to know this last part right here or how to show that. You can prove that since these two, since f grows at the same rate of h and g grows at the same rate of h, then f and g grow at the same rate. This is just analytically showing all the way through. Once you get to this part right here, you could have just explained that they grow at the same rate using the transitive property. Alright, so order and O notation. Not something you're going to use very often, but I want you to have seen it. I don't remember if there are any questions in the book about it. There may be, but it just has to be about whether it's growing faster or not. Let f and g be positive for x sufficiently large. Then f is of smaller order than g as x approaches infinity if the limit as x approaches infinity of f over x, f of x over g of x equals 0, which means what? Going back to what we were talking about, that means that f of x is going to grow at a slower rate than g. And what we would do is write f equals little o parentheses g, and the way you say that is f is little o of g. So if one thing grows at a slower rate than another, we say it is of little o of that function. All right, and of course, if there's going to be an O notation for growing smaller or growing at a slower rate, then there's also going to be a way to say greater. So let f and g be positive for x sufficiently large, then f is at most the order of g as x approaches infinity if there is a positive integer m for which f of x over g of x is less than or equal to m for x sufficiently large. We write f equals big O of g and say that f is big O of g. This is a way of saying that they grow at the same rate. And I know I mentioned just a second ago that there was a way notation for growing at a faster rate, but that's not true. Little o means that one is growing slower than the other, which you can flip around, of course, and put the slower first. But big O means that they're growing at the same rate. All right, that's it.